Bene, allora, dopo un paio d'anni di lavoro qui, vi presento formalmente William Mc Kiver, che lavora con il gruppo dei modellisti applicando il modello SHYFEM e che è un po' l'anima più teorica del gruppo. Abbiamo preso l'occasione della visita di Drice la prossima settimana e abbiamo pensato potesse essere un'occasione per fare un overview di quello che William ha fatto prima di venire a lavorare da noi e del percorso che abbiamo fatto insieme. Quindi la presentazione avrà all'interno non solo le tematiche che ci sono nel titolo che ho mandato a voi, ci sarà più uno. William, se vuoi presentarti da solo, quello che hai fatto.
Ok. Sei in streaming, dovrebbero dargli il microfono in mano.
No, va bene.
Sì?
Sì, lo sto. Sì, lo sento.
Okay, so thank you very much for coming along. Yeah, as Deborah says, so before I actually get into the topic of the talk.
Aspetta, fare l'ultima cosa, perché se non condivido lo schermo, i colleghi che ci guardano da fuori non vedono la presentazione. C'è un delay di 10 secondi, portate pazienza. Eccoci.
Okay. Yeah, so as Deborah says, before I actually get into the topic of the talk itself, I'd like to just give, because I've never given a talk here before, in fact, so, and in fact next week my PhD supervisor, David Dritchell, comes to give a talk, and so I'll be introducing him, and it would seem kind of strange to introduce someone else when I haven't actually introduced myself, so I'm going to give a sort of a brief overview of some of the work that I've done. It's basically my CV thus far before joining the ISMAR here, and then I will get into the actual subject of the talk. So I hope you'll indulge me just hopefully not more than 10 minutes. So the first thing that I worked on, and basically what I done my PhD in, was vortex dynamics. So looking at turbulence basically through the eyes of vortices. And this is something that my supervisor, David Dritchell, is really an expert in the field. And without a doubt, what he presents next week will definitely touch on this aspect of looking at turbulence through the eyes of vortices. So vortices, I think everybody is pretty much familiar with vortices, particularly the most extreme sort of cases, phenomenon being hurricanes and tornadoes that we see are the sort of extreme weather events that people associate with vortices. But they're really things that are prolific even in the ocean as well. They arise as instabilities from the radically driven circulation, but they actually, more than just being instabilities, they're actually drivers of that circulation. Generally, they can be pretty long-lived things, so they're pretty robust. They have long life. Here I show the most exotic, in fact, the longest-lived vortex that anyone knows of. This is the Great Red Spot on Jupiter. So this is an atmospheric storm that has lasted for over 200 years. So this is an extremely robust vortex. But in the ocean itself, there are vortices that have been tracked for of periods of a year or 2 years. So they're also prolific in the ocean. They form a big part of the ocean kinetic energy. About 80% of the total ocean kinetic energy is the vortices. So they're fundamental, basically, to the dynamics that you see in ocean turbulence. The approach I took, and there are various approaches that were done in the University of St Andrews, but for my PhD, really I focused on a very simple idealized model. So considering just a single vortex in QG flow with an ellipsoidal shape. So an ellipsoid, to anyone who is not familiar, is just kind of an elongated sphere, sort of like a rugby ball. So rather than with a sphere, you have a single radius that defines the shape of a sphere. In the case of an ellipsoid, you have 3 axes that define its shape. So it's just a sort of a means to represent a sort of a shape, a sort of oblong shape with a certain orientation. Within the actual quasi-geostrophic theory, this actual vortex has an analytical solution. So you can actually solve mathematically the equation for this individual vortex and then determine its equilibrium. And we've done this and we analyzed the stability of this kind of vortex. And why this thing is actually useful is some of the characteristics that you derive. So the most stable equilibrium that you find for this simple idealized single vortex actually tells us something about the full turbulence situation. So here is actually a simulation that was performed with hundreds of anticyclonic and cyclonic vortices. This is in QG turbulence. And what you find is actually that the typical shape of these vortices, so the typical height to width aspect ratio you find, is exactly that you find in the case of just a single vortex. So though it's a complete idealization, it can actually tell you something about the real complicated turbulent case. You can also, and we did extend this to a multi-vortex scenario, so where you have interacting ellipsoids. And again, although it's a complete idealization, it can tell you, so here I show, this is the full equations, and here is this simple idealized ellipsoidal model, but it can actually tell you something about the shape and the orientation of vortices in what I would call dilute turbulence. So when the vortices are spread out enough that you don't have huge merger of the vortices. So it's an approximation to understanding the full turbulence dynamics. So this was done in QG, so in quasi-geostrophic, but just more recently, in fact, we've solved the case going beyond quasi-geostrophic theory. Maybe some other time I might give a talk on that if anyone's interested. So this is what I worked on in my time in St Andrews. After that, I took a postdoc position in Dublin, in the University College Dublin, where I started to move towards looking at the effect of turbulence on plankton. Now, plankton, of course, is a very important thing, and it's become very important in climate studies because it's really the base of the food chain and also plays a big role in the carbon cycle. So more and more people have become interested in the dynamics of plankton and plankton ecosystems. Now, the work that I've done in Dublin was very much, again, idealized problems. So working with really simple, what we call nutrient, phytoplankton, zooplankton models. So P, NP, and NPZ models. So very simplified equations for the actual ecosystem itself on top of a 2D turbulence equations, the Navier-Stokes equations in 2D. So it's somewhat representative of large-scale ocean dynamics. And really the problem that we were interested in, the focus was really just to look at simply what happens when you change the flow rate, so how strong your flow, your turbulence is relative to the growth rate of your phytoplankton. And essentially that was the focus. And we looked at this for a range of ecosystems, and I'll just give you a very quick overview. So for the very simplest case, so of a simple phytoplankton model with a logistic growth, so no zooplankton, and a simple nutrient concentration field that is a static nutrient concentration, so it's not affected. What you find is, as you, of course, increase the flow rate, you see more and more, so these are the plankton field itself, you see more and more the effects of the turbulent advection. What's interesting is, as you increase the flow rate, not only do you see more the variability associated with the actual underlying turbulence, but you also see a decrease in the average concentration of the phytoplankton. So in a sense, the actual turbulence acts like a limit on the nutrients itself. Now, in this model, this is not particularly interesting, but you can look at some more complicated models. In fact, a slight adjustment to that model where you add zooplankton grazing, what you can find is a scenario where, so in the case where you don't have turbulence, so in the ecosystem solution itself, you can find what's called a bistable solution where you have low growth and high growth for certain values of the nutrient concentration. And what we were interested in was seeing if, not by, in the actual full turbulence case, so when we actually have this ecosystem embedded in the turbulence, if you change the flow rate relative to the growth rate, can you actually substantially change, so move from this part of the solutions where you have a high and a low to the part where there's only a low. So essentially repress the growth. And that's what we found, in fact, by increasing the flow rate, we're able to significantly suppress the growth. So this is like a regime shift, and this kind of thing is you find in things like red tides or whatever, where you have a very sudden shift in an ecosystem. Although this is a completely idealized model, we really was just focusing on if by changing the underlying turbulence, you can actually produce this kind of regime shift. So after my my postdoc in Dublin, I moved to Italy and took up a position at the CMCC, where again I was studying plankton, but really with a much more comprehensive. So moving away from the idealized approach and kind of attacking the problem really with a full-on complicated ecosystem model. So the biogeochemical flux model, basically it models so various phytoplankton groups, zooplankton groups, and nutrients, and the flux of the various nutrients between these groups. So in our model, we actually had 57 state variables, so it's quite a heavy ecosystem model, and computationally is quite heavy. And this was coupled with the Nemo Ocean model, which solves the primitive equations and also contains sea ice and was forced with air interforcing. So this model existed, so this coupling had existed when I started my job at the CMCC. But what we were trying to do was implement a new high-resolution version of the model. So there had been a 2-degree global resolution, but we wanted to move to a 1/4 degree resolution and see how that impacts the ecosystem. So there's a lot of things I could show here, and I tried to just sum it up in a single plot here. Here I plot maps of the chlorophyll during the spring bloom, so monthly means over the spring bloom for the 2-degree, the 1/4 degree, and also comparisons with CWIF's satellite observations. And what we see moving from 2 degree to 1/4 degree, first we see enhancement of growth at the equatorial regions and along coastal areas, which you don't see in the 2-degree model, and is more like what you see in the observations. As well, we were able to reduce a kind of high growth bias that you have in the Southern Ocean in the 1/4 degree. And this is really because we have, in the higher resolution, you have much more vertical dynamics, and you tend to bring your phytoplankton deeper. So you have a deeper mixed layer. You bring the phytoplankton to deeper levels where light is limited, and so you sort of kill off a lot of the growth in the Southern Ocean, which is again more like what you see in the actual observations. Similarly, as well, in the subtropical gyres, which really you don't really see them in the 2-degree model. You start to see this reduction of the bias in the 1/4 degree model. But this is just an overview of this. Again, this is something that probably could deserve a talk of its own. But now, okay, I come to the actual topic of the talk. So thank you for indulging me my summary of my career so far. And start on how we've implemented the non-hydrostatic version of SHYFEM. So essentially the equations we want to solve are the following. So these are the full Navier-Stokes equations basically under a Hydrostatic approximation. And these are essentially written here are what we call the non-hydrostatic equations, because they include the full pressure, so hydrostatic and non-hydrostatic. Of course, we have acceleration, we have a Coriolis term, we have pressure gradients, and we have viscosity terms. But before actually getting into the non-hydrostatic model, it's important maybe to review exactly what I mean by hydrostatic and what that is, in fact. So hydrostatic balance is essentially what happens if you have no flow. So if the flow, there's no forcing, and the flow just relaxes to a steady state, an equilibrium state, then what you get, so going back to equations again, everything here vanishes except for these terms here, the balance between the pressure gradient and the gravitational acceleration. So essentially what that means is that the pressure is just integral from your surface to the level that you're on. So the pressure really only depends on the weight of fluid above the particular vertical level you're at. So you have a stable stratification where density increases as you go down. So you have light fluid over heavy fluid. So this is the static situation. Of course, the static situation is not particularly interesting when you're trying to study the ocean, but what people often do is make what's called the hydrostatic approximation. So in the dynamical case, where you do have flow, you assume that this hydrostatic balance holds. And this, in fact, holds to a large extent. And if you look at the actual equations, particularly the vertical momentum equation, so the vertical acceleration, this holds to a large degree as long as the characteristic vertical scales of your flow are much smaller than the characteristic horizontal scale. So this aspect ratio is less than 1, basically. So if that holds to a large degree, you can make this assumption of the hydrostatic approximation. And for large-scale atmospheric and ocean flows, this is, in fact, the case. So it's an approximation that is widely used, and it's a big simplification, because, in fact, once you make this approximation, you then have pressure defined diagnostically in terms of your density, and you don't have your vertical momentum. So you take this equation out, basically. So you've reduced the problem considerably. So before showing exactly how we implement the non-hydrostatic solution, I'll just give a brief summary of SHYFEM, and I think most of you are familiar and probably have seen and heard much about this model. Originally, this was developed for the shallow water equations. More recently, it has been modified for the primitive equations, so for the equations where you assume hydrostatic balance. It represents horizontal transports, so the U and the V on elements, while salinity, temperature, and the vertical velocity are defined on nodes. And also, in fact, well, when we come to the non-hydrostatic pressure, it also is defined on nodes. Previous implementations of the model were all assuming hydrostatic balance. And so we've just recently updated the model to include non-hydrostatic effects. So how do we do it? So the approach we take is what's known as the two-step approach, where you divide your pressure into a hydrostatic part and a non-hydrostatic component. And this is following the work of Cazzoli, who originally introduced this methodology. And so you do the problem in 2 steps. Basically, your first step solves just the hydrostatic solution, followed by a second step where you solve for your non-hydrostatic pressure and then use that to adjust the hydrostatic fields. So this is really a semi-implicit approach. So by semi-implicit, it means where you take one of your variables and you define it in terms of, here n represents your time step. So x of n here is your now time step, if you want, or your current time step. And n plus 1 is your next time step. So you can divide your variables between its value at the next time step and its value at the current time step, depending on some weighting parameter we call alpha that ranges between 0 and 1. So when alpha is 0, effectively this means it's fully explicit. So you just have your now part of the variable. And in our equations, the advective, the Coriolis, and the viscosity terms of the horizontal momentum equations are all treated explicitly. If alpha is equal to 1, you have what's fully implicit, so that the variable depends completely on the next time step. And in our application, we use the vertical component of viscosity in the vertical momentum equation is fully implicit. As for the semi-implicit terms, so this weighting can take any value between 0 and 1. And in our case, it's for the SHYFEM, we use semi-implicit for the horizontal divergence term in the continuity equation, as well as the hydrostatic, and of course the non-hydrostatic pressure, because fundamentally we want to do this two-step problem. So when you discretize the equation using a forward differencing, the equations look like this for the first step. So this is for the hydrostatic step, and here I use a tilde here to indicate that this is just the hydrostatic step, so the first step, so not the full solution. But here we have our advective terms, which are completely explicit, as well as the horizontal viscosity terms. The pressure, so the hydrostatic pressure, you have the semi-implicit, so you have the current time step and the next time step part. Whereas for the non-hydrostatic pressure, at this point, you only have the explicit part of the non-hydrostatic pressure. So you iterate or solve this equation, and essentially this is the hydrostatic step. So you're really solving the hydrostatic problem. So the next step involves making the correction using the other part of the non-hydrostatic pressure. So this is the part at the next time step. And this will give you then the final flow field. So you're basically your non-hydrostatic solution. But of course, at this point, we don't know what the non-hydrostatic value is at the next time step. So you have to obtain an equation for that. And to do that, you can substitute this into your continuity equation. So the incompressibility, the divergence of the velocity. And what you obtain is the following. So you have the Laplacian of the non-hydrostatic pressure is related to the divergence of the hydrostatic velocity. So this is the one that you solved in the first step. So it's basically a Poisson equation, Poisson type equation. And this can be represented as a linear matrix system, which you can solve using various matrix solvers. So we use a sparse bit solver to solve this equation. And once you've that, you've solved the non-hydrostatic equations. So to the actual test of this non-hydrostatic solution. So it sort of checks to see that we're in fact actually solving the non-hydrostatic equations correctly. So there are a number of different scenarios where the non-hydrostatic effects are important, and there's a clear difference between the hydrostatic and the non-hydrostatic. One of them is the case of in fact, I lost the header here, but this is a case of a standing wave in a deep basin. So we have a square basin, so 10 meter by 10 meter basin. You initialize your free surface as follows. So you have a sort of a disturbance, initial disturbance at the free surface. And then you basically look at the time evolution of this. And you can actually obtain an analytical solution for this problem, which we can use it as a validation basically for the model. So looking at the solution, so here I plot the free surface as a function of time at the two ends of the tank. So for both the hydrostatic, the non-hydrostatic, and also the analytical solution. What you see, so the blue line here is the hydrostatic, and clearly it cannot represent the observed oscillation that you find in the tank. So there's an extreme limit really to the hydrostatic model in this case. Whereas the non-hydrostatic captures the analytical solution very well, although there's slight amplitude differences as the simulation goes on. But it's a clear test where you can see that you need the non-hydrostatic processes. So the other test that we looked at is another classic sort of water tank experiment where you have basically water of two different densities initially separated. You then pull the barrier out and then see sort of a gravity current that moves along, so the heavy fluid moving along the bottom at the same time the lighter fluid moving at the top. And what you see in whether you apply hydrostatic or non-hydrostatic is quite different. So here I'm going to try and no. Okay, if you can both.
This is the hydrostatic.
Yeah, or I can go with the hydrostatic first. So here's the solution for the hydrostatic. This is a density anomaly, how it evolves. And what you see is a very, I would say, artificial square front at of the density curve as it evolves. Something that you wouldn't really expect to see in the real experiment.
Was not shared with the others.
Do you want to try it again?
Let's continue then.
Okay, so for the non-hydrostatic case, what you see is you see a curved front, but you also see this Kelvin-Helmholtz instability or roll-up of the density field. So this is really what you would see in the actual in the water tank experiment. So clearly, there's a big difference in whether you include the non-hydrostatic process or not in this experiment. Any questions? Okay.
The solution depends a lot on viscosity of this thing.
Well, in the case of the locked exchange, we use minimal viscosity. I mean, in fact, I won't say inviscid, but
And how much was the density difference?
the percentage of the
Yes, the density difference between the two.
it's very simple. Well, the salinity. So we're talking about fresh water and a salinity of 1 point. Yeah, so it's a very small.
3%.
Yeah, it's I can't remember, but it's a very small gradient of density, in fact. So those are. Okay. Okay, so those are our two tests basically, or checks, I suppose, on our non-hydrostatic SHYFEM. So now I'll turn to how we've just started to apply this, looking at the dense water reproduction in the Adriatic Sea. I should say that this is really preliminary, so I don't have a huge amount to say. So a lot of you might be familiar with, probably some of you who are involved in some of the measurement campaigns, a very strong dense water event that took place in 2012 between January and February there was a very strong Bora wind that induced record-breaking density anomalies, so of the order of 30. And this, in fact, is what we're going to focus on. So this exact dense water outbreak that we're going to look at. So this was triggered by the strong Bora winds, but it was also because of there had been a reduction in the freshwater input in the year before. So there was sort of a preconditioning that led to an extreme outbreak of dense water in it. So the dense water was formed in the northern basin and then propagated southwards. So it's been studied, this event and dense water events in general has been studied in many observational and modeling studies. Our particular take or focus is really to just look at if including these non-hydrostatic processes is important from a modeling perspective. So can you apply the primitive equations where assumed hydrostatic balance, or do you really need to use the full non-hydrostatic equations? So that's really our focus here. We use, so I'm going to show some results from the SHYFEM, but also from the MIT model, because when we originally studied this problem, we didn't actually, so when I started the job here, we didn't have the non-hydrostatic version of SHYFEM. And so I'll also show some of the results we have. This is with a collaboration with John Maria Zanino from ENEA. And I kind of divided up, so starting just looking at the impact in the northern Adriatic and the shallow basin, and then showing some results in the southern Adriatic, and particularly around the southern Adriatic location. So in our first look, basically in the northern Adriatic, well, originally what we were looking at was a model into comparison between SHYFEM and the McGCM to see how each of the models represent the actual formation. But the McGCM actually was already had a hydrostatic and a non-hydrostatic version. And so I will show you some of those results in the northern Adriatic from the MIT model. We used surface forcings from meteorological forecasts from Moloch. We have temperature and salinity at the open boundary at the Otranto Strait from AFS data. We have tidal from Otis and AFS sea surface height data. And the river inputs were from ARPA and the Regione Friuli. So as an overview, and you can look at lots of different ways at this to try and present how the difference between hydrostatic and non-hydrostatic. Here, I show surface vorticity. Here, the top panels are actually for the hydrostatic. Sorry, I haven't written here. This is the McGCM hydrostatic simulations for different times. So this is before the actual the Bora event, during the Bora wind, where you can see a strong enhancement of the vorticity field, and then after actually I have them here. So here's 26th of January, 5th of February, 16th of February, and then the 27th of March, which is long after the wind event. The bottom panels, what I show is directly just the difference between the hydrostatic and the non-hydrostatic fields. And what you can see really in the northern basin, there is almost no difference between the hydrostatic and the non-hydrostatic dynamics. So in the region where you have the dense water formation, in terms of the circulation itself, there's no difference. Although I note that as you move further south, you do begin to see differences in the vorticity.
When you say vorticity,
I mean the vertical component of vorticity. Yeah, sorry. In fact, every time I say vorticity here, I just mean the vertical component. Yeah. Also, So here I show some depth profiles, or time series of the depth profiles. These are averaged over the shallow basin in the Northern Adriatic. So in the part of the basin where the depth is less than 40 meters, we've averaged basically these fields. So what you can see in the density anomaly, here I have the hydrostatic and the non-hydrostatic, and here I have also root mean square vorticity, hydrostatic and non-hydrostatic. Well, you can see in the density anomaly, obviously you can see the formation of this density, strong density anomaly after the Bohr event. But in comparison of the two, so these are extremely similar. So for an average over the entire basin, you really see very little change between the hydrostatic and the non-hydrostatic molecule. Also, just I showed the surface vorticity field, but if you look at vorticity to deeper levels, so the vorticity field is a real marker, I guess, for the actual Bohr event. So you see the enhancement here, but you see absolutely no difference between the non-hydrostatic and the hydrostatic. So really, there's no impact in terms of the dense water formation on using the non-hydrostatic dynamics.
What does this mean?
What does that mean? Well, if we go back to where I talked about where the actual hydrostatic balance applies, and the fact that if you have characteristic vertical scales that are much smaller than characteristic horizontal scales, then you can neglect your vertical acceleration and you can assume hydrostatic balance. So I think in a way this is not unexpected, because we are talking about a shallow basin, but we're also talking about strong horizontal dynamics. So you have strong vortical structures that are fairly big.
I don't want it to.
Yeah, no, it's not spoiling. In fact, that's practically the reason that I would say is that because of the constraint in the vertical dynamics, the constraint in terms of the depth that you have in the shallow basin, it's not a huge surprise perhaps that non-hydrostatic doesn't play a part there. So moving from the Northern Adriatic, then what I want to look at now is what we're kind of currently in the process of looking at is using SHYFEM and kind of focusing on the Southern Adriatic, where we expect to find more impact of the non-hydrostatic effects. So here we have implemented so a slightly higher resolution version of SHYFEM, really, and it's hard to actually see here, but we've tried to resolve more around the Southern Adriatic pit. So higher resolution here to try and resolve some of the dynamics here. We've currently ran this with 59 levels for the hydrostatic and non-hydrostatic. We've ran a simulation for 99 levels for the hydrostatic, and we have currently running a case for the non-hydrostatic with 99 levels. Unfortunately, I can't present anything about that, but I'll talk a bit about that. So our simulations, it's same as before, using the same forcings that we used. And also, I'll make some comparisons with some of the observations that were obtained in the ODW campaign that was done around the Adriatic, Southern Adriatic pit. So first, just looking directly at the non-hydrostatic pressure. So the non-hydrostatic pressure field that we get out of SHYFEM, where do we expect to see strong non-hydrostatic effects? Well, the SHYFEM, like McGCM, also suggests that there is no real non-hydrostatic dynamics in the shallow basin in the north. But what we do see is much stronger values in and around the Southern Adriatic pit. So this is kind of part of driving us really to look specifically at that region. When we look at our simulation, so here is kind of a slight overview. In fact, it's not, should have done a difference between these because it's not very clear. But if you look at the density anomaly, this is our time average and average over the vertical as well. You do see differences in the density anomaly field between the hydrostatic and the non-hydrostatic in the actual, in the pit itself. You also see differences, strong differences in the vorticity field in and around the Adriatic pit. In fact, you see much more smaller scale vortices here, and these are linked, in fact, to more vertical dynamics that you have in the non-hydrostatic. So in terms of kind of validating or comparisons with some of the mooring data, so here, these two plots, this is the hydrostatic, this is the non-hydrostatic. I'm showing blue lines are temperature, green lines are current speed, and the thick lines are the simulation, and the thin lines are the observations. So what you see, in fact, you actually, the hydrostatic seems to actually represent the mean values better than the non-hydrostatic at this mooring. But one of the things you do see in the non-hydrostatic, even though that the mean, there is a bias in the mean value, what you actually see is much stronger variability. So here, looking at the temperature of the non-hydrostatic, you have much more variability than you have in the hydrostatic field, and this is more similar variability that you see in the actual observations.
Will?
Yep.
Maybe suggest that you point out the number, because I can see from here, but probably
so the temperature here, the range here goes from 12.6 degrees to 13.6 degrees. Here we have velocities going from 0 to, sorry, these are speeds of velocity. Speeds going from 0 to 0.8. Looking at salinity also and the temperature fields, so here we have temperature at two different sensors at different depths. And in fact, the hydrostatic, the mean value is more representative of the actual observed value. So the observed, sorry, I should say here the blue line is non-hydrostatic, the green line is hydrostatic, and the red is the observed. So the hydrostatic actually, in terms of mean value, represents better the actual observation at this mooring. But again, the variability of these fields, which varies much more frequently than the hydrostatic, is more reminiscent of what you see in the case of the observations. Looking at a different mooring, so looking at two other moorings. So here, this is the mooring DD, and this is FF, and the salinity fields. Actually, at these moorings, you see that the non-hydrostatic model is more representative of the observed, and you have a bias in the hydrostatic case. Here, showing also green roses of the actual currents, you see that you have a better representation of the magnitude of the flow. So this is like the cascading that you see on these on the Southern Adriatic pit for these values, although actually at the F, the hydrostatic is slightly stronger here. So I would say, as an overview, in terms of comparison with the observations, I can't really just say the non-hydrostatic improves what we see. It's a mixed picture, really. Certain moorings you see an improvement with the non-hydrostatic, and other ones the hydrostatic does better. But overall, the variability in the non-hydrostatic seems to be more representative of the kind of variability you see in observations. And the last thing I want to show, so I mentioned that we'd run the hydrostatic at 99 levels. And just, this is a comparison now of the two hydrostatic simulations. We don't yet have the non-hydrostatic simulation with 99 levels. But even in the hydrostatic, you can see an improvement in the results, just moving to higher vertical resolution. And what you would expect, so this, going from 59 vertical levels to 99 vertical levels basically means that our maximum layer thickness goes from 50 meters to 17 meters. And this is very important when we consider that we're talking about in the actual southern Adriatic pit, we're talking about a depth of 1,200 meters. So really resolving the vertical dynamics is very important, and in fact is even more important, because in fact in the non-hydrostatic, really vertical dynamics play an even bigger role. So potentially this is going to be very important for the non-hydrostatic simulations, but at the moment we don't have that yet. So to conclude, we have implemented the non-hydrostatic version of SHYFEM. We've tested it, and we're starting to apply it now in the Adriatic Sea. In terms of what we see in the Adriatic, basically the picture is in the northern shallow basin, there's no impact of non-hydrostatic processes. So if you're simulating something in the northern Adriatic shelf, you don't really have to worry about the effects of non-hydrostatic processes. But as you move further south and around the Adriatic pit, you do see big differences in the dynamics that come out. You see differences in the density anomaly, you see differences in the flow field, in the vorticity field. So there is a big impact. In terms of validating or saying which is better, as I'd already said, it's mixed picture depending on the moorings or the observations you look at. But the one thing I would say is there is greater variability in the non-hydrostatic simulation. So something more variable that is more representative, I suppose, of the true observations that we see. And finally, really, it would be good to see how the increase in the vertical resolution affects the non-hydrostatic simulation, because in the Adriatic pit, in this kind of deep basin, you really need to resolve in the vertical. And the last thing I'd say, so in terms of future work, we'd like to look at modeling the dynamics of scour holes. So there's a different scale of problem, really. So scour holes in the Venice Lagoon, and see again if there's any impact of including non-hydrostatic processes there. Also, looking at these G3 groundwater springs in the Mar di Taranto, where you have gravity flows. Again, it could be a problem where.
Yeah, there are different processes there.
Yeah, sorry.
It's just.
Yeah, this is okay. But anyway, there are things that where the non-hydrostatic could also play a role in the dynamics. And finally, I guess tying up with basically my own background and what I've done previously in the work I've done in St Andrews, it would be nice to try and implement a study of ocean vortices using both the full equation, so from the non-hydrostatic SHYFEM, but also using these idealized models where you can get analytical solutions and trying to find ways to understand better the characteristics that we see in turbulence in the ocean. So I'll leave it there. Thank you very much.
Should we stop the streaming and then continue with the questions?
Yeah, I don't mind.
So, anyone?
Yeah, I was wondering if you consider that the southern Adriatic is also a place of dense formation by convection. So maybe the convection process can be one of the reasons that you see a difference in the impact of the non-hydrostatic.
Yeah, no, that's.
So it's not only cascading.
It's not only cascading. I think, in fact, and I'm sorry about the image of the density anomaly, but actually what you see is you have a stronger anomaly in the eastern part of the pit. So maybe not just associated with the propagation of dense water from the north along the western part, along the Italian coast, but also, as you say, there may even be an impact because of the convection. So
the main reason is the shallow depth in the northern Adriatic. The reason why we don't see that much difference.
That's what I.
During convection, you have very high vertical flow.
Yeah.
No, not only shallow, maybe. So just because the flow was mainly horizontal. So
yeah.
I guess even if the northern area was much deeper, we should expect the same results.
There's another thing, another limit on.
Not.
Yeah, I should say, because I stress that this like aspect ratio, basically the ratio of the vertical and horizontal scales is a limit on your vertical acceleration, basically the non. But there's also a limit if you have geostrophic balance. So if you have strong geostrophic flows, and that in fact is another limit. That would also, so you could have deeper structures, but if you have small Rossby numbers, you limit the vertical acceleration as well. So that's a good point. And in fact, that's probably something that's worth checking in terms of attribution, whether it is the vertical scales or geostrophic balance that limits the impact of non-hydrostatic.
Do you have any explanation about why there is this bias between temperature and salinity in the hydrostatic?
Not at the moment.
Well, some options.
If you want to.
One point is the non-hydrostatic and the hydrostatic approach. The other one is the capability to match the vertical dimension of the process that is driving the mixing of water. And as William was saying, the use of the run with vertical resolution of 50 meters means, in terms of the dense water tongue and how it propagates, that everything happens in the last layer without any reproduction of the vertical structure of the bulk of dense water. And it is probable that the non-hydrostatic simulation with the 99 layers, so with a higher vertical resolution, would provide better results and then match better the temperature and the salinity. The bias is not everywhere equal. So it is more connected with the small-scale processes happening all around the peak, close to the canyons and also western part, than on general overestimation of the variable.
I guess that this variability in the bias can it be kind of a tool to try and see what is the reason why there is bias and what are the processes that are differently represented by this approach. Because, I mean, for instance, we've seen that the results in the sea mooring were pretty good for the hydrostatic model as well. So, and in the sea mooring, there is a strong component of cascading. Besides some deep part coming nearly just rapidly from the bone. So probably, I guess that the part of the salinity bias in that and B might be the result of some integrated processes from the taking place along the slope and probably due to mixing, but related to the gradual downflow, instead of the cascading problem. I mean, just a possibility, but it's a thing that I think it's pretty apparent from this.
No, it's I mean, I think, again, what Deborah says, I think part of the problem with how we apply the non-hydrostatic now is that by not resolving completely the vertical, so we have an extra sort of degree of freedom. Now we have the non-hydrostatic, we have vertical acceleration. But in fact, we have vertical acceleration, but we have 50 meters in the bottom layers in the Adriatic pit. And so, in a way, it's a waste almost of those extra degrees of freedom that you have by not actually resolving that degree of freedom. So what we hope is to see something as a holistically speaking in terms of, because of course matching at moorings as well can often be difficult when you have But I think from the vorticity field, what is clear is you have more smaller scale structures in the non-hydrostatic, and that of course leads to more variability. So, but yeah, it's definitely a good point.
Can I ask something to the audience? So the guys that were in the, I was in some of these field campaigns, but my question is, all the processes happening on the western side of the pit, that were the one that were not investigated by the moorings, because in that case we were more interested in looking at the dense water flow coming from the western, all the small structures that we see on the eastern side of the pit and that are not monitored seem to me really interesting because in a way that the structures are modulating the flow coming from the middle Adriatic pit, and so water that is less dense, but that interact with all the southern Adriatic circulation. Are you aware about other studies, other evidences connected with that small structures? Just a little question.
Sounds like a no.
Someone mentioned cascading.
Yeah, the cascading is more connected with the canyons pathways.
So yeah, where the dense water comes along the Italian coast, and then you have cascading, and that's where these moorings, where there are observations, are along the western side of the canyon, of the pit.
But then it seems that there is an overflow bordering all the eastern part that probably has some preferential waste, but that is more diffused. And then that can be motivated also by that small scale structures.
Well, is there any vorticity modulated by the entrance through ultrasound?
Well, it's possible, yeah, that you have effects at the boundary. Modulation of the cascading, well, I would say that the most part of that is related to the dense water generation itself. And the dense water generation, which can happen also on the eastern side of the canyon, but is related to the forcings and the swing event. So, I mean, I won't say that there's no impact of the boundary, but hopefully it's well, I would just say that there's no reason to expect it to be more or less in hydrostatic or non-hydrostatic.
A general question, because I have no physical perception of the quantity involved. This dense, the bottom dense water level, because you mentioned the resolution of the model. Mm-hmm. How thick is my perception of this layer? This water. To say stupid thing, yeah, 1 meter, 10 meter, 50 meter. I have no idea.
Yeah, so.
Yes, of course, but here,
you mean in the pit, or
the thickness is increasing along the pathway of the cascading. So for employment, the thickness of the tongue is increasing, but let's say as an average of 30 meters is something that I read about.
It's not a steady process. So
no.
Changes with height.
How heavy is the non-hydrostatic computer time?
It's terrible. I didn't say all the downside from a computational point of view. I don't know. It's maybe at least 4 times, or maybe that's even being generous. Yeah, I'd say about 4 times slower than the hydrostatic. So you pay a big price computationally for including these processes.
But we'll paralyze also that part, right?
Well, yes and no, because if you have a parallelized, we still don't have solved the problem of the implicit part. Because the parallelization right now is only for the explicit part, and the solution of the Poisson equation heavily relies on the implicit part. So there's still quite some way to go. But we hope we can do it.
Yeah, we can definitely need that.
Sorry, William.
Yep.
This is the SHYFEM result.
Yeah, these are, so everything I showed for the Southern Adriatic were SHYFEM.
What about MIT?
Oh, I haven't looked at it in terms of the Southern. So why I showed the results before is because originally when we did this modeling comparison, we had the non-hydrostatic MIT model, and so we looked basically at the impact of non-hydrostatic in the Northern Adriatic with that. So, but now that we have the non-hydrostatic SHYFEM, but I suppose it might be interesting to see.
I was wondering also for the bias problem.
Yeah, it might be. Look, I'm not sure. Well, hopefully I still have the results from the non-hydrostatic SHYFEM run. Like so, yeah, it might be worth to see how that model deals with this cascading. Yeah, no, it's maybe should look.
About the bias, did you check the differences before the event?
But there is that is that not the time? I think there's a time. Actually, no. This is after the event. Okay. In fact, this is the time when the actual dense water arrives.
So before the event, you should expect that the two models agree at a certain point.
So looking just because in fact you don't have observations for before.
I don't have observations.
Yeah, but
You have models.
that's a point to look at.
No, because it could also be that the hydrostatic mix is too much, and the bad performance is given by the non-hydrostatic model. Depends on the initial.
Yeah. No, we could look at the difference. That's a good point. Look at just the difference between the models to see if there's, before the actual arrival of the dense water, if there's more convergence between the two, and then this itself. So that's definitely something we should look at. We don't have any model comparison to make, but
terrible. Maybe the mistake is given by that. So the initial conditions in this case are quite important, and the atmospheric forcings of the wind temperature.
But that are equal to both. So
Yeah, before, but you don't know whether or not the initial condition from your Adriatic.
okay.
You don't know which is at the beginning there was a bias or not.
but
If we are talking about the two SHYFEM simulation,
Yeah, but a comparison with observations.
okay, for sure, but in that case, the bias would be introduced in both run, and that for sure can
Yes, but
evolve in different ways.
you are saying that at that specific moment, the hydrostatic gives better performance, but the whole history is not known. So
We will check the whole period.
Yeah,
it's a fake. So
although it should just be said that we are talking about differences of 0.2 in the
you should expect
salinity.
some bias in your initial condition too. So
Well, I mean, the initial condition is the same in salinity for both models.
Yes.
You might be having a bias, which is apparently correcting the previous bias. No. So you may have an initial bias, and then during the event, you may be producing with your model an additional bias, which is compensating the previous one.
Okay.
So the agreement may be.
But only in the case of the
We don't know.
non-hydrostatic, not in the hydrostatic, you're saying. Okay.
Just a kind of.
If you will use a different initial condition, you could basically compense for the bias you see.
Yes, but
Yeah.
Yeah, but the nice thing is that you really get the curve. I mean the oscillations.
Quite right.
Yeah, right.